All right, welcome to 6.4 day 2. This is the rational exponents. And remember, just rational exponents are like fraction exponents, like 3/4, stuff like that. And so we're doing like these simplify expression questions. So we have to remember our exponent rules, and then also how to switch forms. So like this one, remember, would be let's see, it'd be a fourth root because the tree roots go down and the power lines go up. So this would be a power of 3 and a root of 4. So oftentimes when we're simplifying on these, we're going to switch forms between the rational exponent and the radical form. So we're going to pick up where we left off, which was just going through examples. What's hard about this is, again, you got no exponent rules, you got no fractions, and then each problem is a little different. So it's not like I can give you formulas or steps. Other than oftentimes when you get stuck, the right thing to do is to switch forms. All right, so that'll come up a decent amount in some of the questions we're going to do today. And this is just a continuation of part 1 of this lesson. So I'm going to skip to where we were, which was not there, this one. All right, and so some of them you can just do on your calculator, right? So this is a particular example where we can do it on our calculator. So if we want to do 16 hat thing, negative 2.5 power, right? We get some crazy looking answer, and oftentimes they're going to want a fraction on this. So one quick trick on this, if you have a graphing calculator like this, is you can hit math and do number 1, fraction, and that'll take your previous answer and turn it into a fraction. So it looks like our answer is actually 1 over 1024. Right, so we know from our calculator this is 1 over 1024. Right, but if this had an x in it or something, you couldn't just do your calculator. So let's see if we can do it with the rules. First thing is to remember what a negative exponent, you move it down and make it positive. So this one sort of flips, and we're saying 16 to the negative 2.5 is like 1 over 16 to the positive 2.5. Right, so that's how you deal with a negative exponent, is just move it from the numerator to denominator, or vice versa. Next up is to know that 2.5 is really like 2 1/2, which is really like 5 divided by 2. 2 is 4 halves plus 1 more half, so we have 5 halves. So I'm going to rewrite this as 1 over 16 to the 5 halves. Okay, and then I think I talked about it in the previous video. If we switch forms here, we can clean this up. So we can do, let's see, the root would be 2, so we'd have a root of 16 to the 5th. And this is nice and neat because if we do the root part first, the 2 root, the square root, we'll get 4, and then do 4 to the 5th power, and we get 1024. Okay, so it's kind of easier just to do it straight on the calculator, but I thought as the problems have x in them, you'll have to do them this way. So there's an example. Okay, I would encourage you to pause it and try everything you can on this one. This is a 3/4 exponent, or sorry, negative 3/4 if you can't quite see that. So give it a shot and then unpause and see the solution. Okay, so this exponent rule, you actually distribute that exponent on the outside. So if I have a 2 here, we kind of distribute it, and then we do power of a power to get x to the 4th, y to the 6th. So you end up multiplying 2 to these exponents. So in this case, this negative 3/4, we're going to apply it to both. Okay, and please note that if you wanted to do flipping, you could, right? Remember on the previous question, we moved exponent down or up. And you could do that here, but it'll work out kind of nice on this one because we'll do negative times negative for y, and then you'll have a positive exponent there for y. So distributing is kind of helpful in that sense. All right, so next step is I'm just going to do just what I was talking about. I'm going to take and multiply those two because it's power of a power. So I'm going to take negative 8 times negative 3/4, and that'll give us 24 over 4 or 6. So that cleaned up really nice. So now this y just has a positive 6. All right, we don't want to leave our answer with a negative exponent, so we're going to move that down, but the y to the 6 is going to stay up top. All right, it's a positive exponent, so it just stays in the numerator. Okay, and now we're going to do just like we did on the last question, where if we switch this forms, it would be a fourth root, right? The root is the bottom number, the 4. The power is 3. So we'll have y to the 6th, and then the fourth root of 16 is 2. And then if we cube 2, we get 8. So all this comes out to be y to the 6th over 8. Right? Kind of cleans up nice and neat. But it's a lot of different rules there, a lot of exponent rules, and a lot of fraction work. All right. Next one, again, this is a 2/3 power if you can't quite see it there. I encourage you to pause the video, give it a shot before continuing. Actually, yeah, maybe I should give you the first step too. One of the tricky parts about this is we've got a radical and a fraction here. So it'll probably help if we rewrite that xy as a 1/2 power, right? A square root is like a fraction of power of 1 root of 2. All right, so maybe you can get it from there if I give you that first step. Okay, so next up, we're going to distribute the exponent. You wouldn't have to do the steps in this order, but to me, this is what would be the logical next step, is to distribute that. So all the bases, the 8 gets it, this x gets the 2/3, and then the little xy grouping there, that's to the 1/2 power, and now that's going to get raised to the 2/3. Okay, so we're going to do like we did in the previous question. This becomes power of a power, so we're going to multiply those. All right, and that'll come out to be 2/6 or 1/3. So all we did was this power of a power, so everything else I'm going to keep the same for now. So this is going to be xy now to the 1/3 power. Okay, now I'm going to dump that 1/3 in there. And actually, I'm going to do two things. I'm going to distribute that, and then also I'm going to switch forms here, like we did on the previous question. So I'm going to make it into a third root of -8, and then square. Okay, and this you could just type that straight in your calculator, right? 8 to the 2/3 power, that would be fine. Okay, and then we have x to the 2/3. And so now when we distribute, we'll have x to the 1/3 and y to the 1/3. All right, so this part will clean up nice and neat again, because it'll become the cube root of -8 is -2. All right, and then we're going to square that, and eventually we'll get a 4. Here, we're going to add our exponents because they're the same base multiplied. So we just add them, and we're going to get x to the 3/3 or 1. All right, 3/3 is just 1. And then we have y to the 1/3. All right, and that's our final cleaned up answer. All right, pretty tricky, but yeah, each question's a little different. So homework, give them your best shot. If you get stuck, always reach out and just ask questions if you're not sure how to do the homework questions. Okay, so the final thing I got is students are always asking me, Mr. Westpatel, this stuff, this last question we just did, when am I going to use this? This looks like pure gibberish to me. And one of the examples I read in a book once, where these weird exponents were doing like fractional exponents. So technically these are decimals, but it's the same concept, I guess. Is someone figured out in baseball that in general, a team's winning percentage is based on how many runs they score and compared to how many runs they give up. Right? Basically, the more runs you score, the less runs you give up, the better your record's going to be. And they said your winning percentage is this little formula here, approximately. Okay, and since there's been years and years of baseball statistics, they can say that this is actually a pretty accurate way of predicting how many games a team will win. So I brought up, this is the 2019 standings where the Twins hit all the home runs and had a pretty good record. Here's how many runs they scored. Here's how many runs they gave up, runs against, and their differential. So you can see the teams with good winning records have a positive differential. And then if we look at Detroit, who did not win many games, they gave up way more runs than they scored. So I think an interesting question is like, did the Twins kind of get lucky this year or not? And so we can compare the winning percentage that they actually had with the winning percentage that they should have had according to our formula, right? And so basically we can say, okay, we know this is their actual winning percentage from that year, but we can plug in they scored 939 runs, right? And then divide that by the runs scored again, so 939 to the 1.83, almost squared. But they found that they tweaked the numbers and they found that that's the right exponent. It's not 2, but 1.83. And then the runs against is 754 to the 1.83 power. Okay, and so now we just got to do these numbers on a calculator and calculate the winning percentage. So 939 hat thing 1.83. There's our fractional exponent or decimal exponent. So I got to remember that number. 275,409. 754 hat thing 1.83. All right, I'm just going to copy that. Okay, and so now it's just more crunching. So now I'm going to just do this in my calculator here. Add the 2 on the bottom and then divide the 2, and I'll get the winning percentage predicted by the formula. Okay, so you can see their winning percentage here should have been about 60% according to the little formula. So we got about a 60% winning percentage, or 0.600. And you can see that they won a little bit more than that. So the formula was pretty accurate at predicting their win percentage, but they actually got maybe a little lucky this year. Based on the runs scored and runs allowed, they were about a 600 team, 600 winning percent, and they actually won a little bit more than that. So I thought it was kind of an interesting idea. In baseball, they've got so many cool applications of math and statistics. They've figured it out to, they can predict at the start of the year based on certain players. If there's not injuries and stuff, they can have a pretty good guess at who's going to be the teams in the playoffs and who's going to be the teams that don't make it. So I thought that was an interesting example of rational exponents in real life. All right, that's it. Thank you for watching.